Hello and welcome to today's webinar. My name is Heidi Barnes and I'm product owner for Power Integrity EDA tools here at Keysight Technologies. We have some great content prepared for you today. Now on to the presentation. At DesignCon 2020, I had the pleasure of working with Steve Sandler of Picotest and Jack Carroll of Xilinx to show a practical method for measuring dynamic switching current of an FPGA power rail. The results were better than we expected. Not only did it work, but it also showed us how to find worst-case noise on a power rail. Here in the upper left is the Zinc UltraScale ZCU104 board that was used for the measurements of dynamic switching current at the FPGA. And in the upper right, a picture of the PathWave ADS PI Pro setup for EM simulating the main VCC INT power delivery network to the FPGA. The methodology used to extract dynamic current from voltage measurements showed that predicting worst-case noise is not intuitive. One would expect that toggling the FPGA at a higher frequency, like 200 megahertz, drawing 13.5 amps DC, shown in the graph on the left, would have more noise than for the lower power case of toggling the load at 30 megahertz with only 2.5 amps DC, shown in the graph on the right. The graph on the right clearly shows that the worst-case dynamic current and voltage noise is happening at 30 megahertz, not 200 megahertz. The voltage was easy to measure with high-impedance probes, but how did we get the dynamic current? There is no available current probe that fits on or around all of the FPGA power pins. The methodology used for obtaining the dynamic switching current is to rely on the easily obtained dynamic voltage measurements. Here is a simple schematic that shows voltage and current going into a PCB power delivery network, aka PDN, and the voltage and current coming out into the load. By applying measured dynamic voltages simultaneously at the input and output of the PDN impedance matrix, the PathWave ADS transient simulator is able to synthesize the corresponding dynamic current. This method is quite simple in concept, but there are a few details that you will need to know if you want to measure dynamic switching current on your next design. The rest of the video will step through the details of how to build an accurate model of the power integrity ecosystem and how to take the dynamic voltage measurements that make this a success. Here is the outline of what will be presented, starting with a description of the load transient generation and the method of connecting a benchtop supply for easy DC current monitoring. Next, the details of obtaining models for each part of the power delivery ecosystem: PCB, capacitors, VRM supply, and FPGA package die model. Then, with these validated models of the PI ecosystem, simulations can be used to validate the measurement methodology for dynamic switching current. The results are demonstrated for the particularly interesting case of finding the worst-case power rail noise. Here is the basic description of the power integrity ecosystem that delivers power to an FPGA provided by Jack Carroll of Xilinx. The power travels from the voltage regulator module, aka VRM, through the printed circuit board to the FPGA package connections. The FPGA package substrate then carries the power to the die. Decoupling capacitors are used both on the PCB and inside the package to provide delivery of clean power at frequencies that are higher than the bandwidth of the VRM control loop. The very popular Xilinx ZCU104 evaluation board for video processing was selected as the example application for this presentation. This board uses the Xilinx Zinc UltraScale Plus ZCU7 FPGA and can draw up to 30 amps on its main VCC INT power rail running at 0.85 volts. Min-max recommended operating voltages give a margin of 51 millivolts peak-to-peak switching noise ripple. The VCC-INT power rail must be able to maintain the desired 0.85 volts with minimum noise ripple to the FPGA under all load conditions. To verify that the power delivery network can handle both step load and steady-state switching noise, the FPGA was programmed to create a dynamic load. 400,000 registers were programmed to toggle at different clock rates. The faster the toggling rate, the higher the current. At 1 megahertz, the step load steady-state change in current is only 50 milliamps, while at 330 megahertz, the steady-state current increases by 20 amps. The control is done using the Xilinx Vivado Lab Control Panel software, shown here running on a laptop. It uses a serial USB connection to communicate with the FPGA on the ZCU-104 evaluation board. The control panel cannot directly measure the current, but it can read the temperature, which provides an indirect indication of a change in steady-state current. To simplify the measurement of the dynamic load, it helps to have a bench supply connection to power the VCC-INT power rail instead of using the point-of-load VRM installed on the ZCU-104 board. The bench supply will make it easy to monitor the steady-state DC current, provide a lower noise power supply connection, and removes the complexity of sense lines from the control loop behavior. The biggest challenge with connecting a bench supply to the high current VCC-INT power rail is that the bench supply cables have a lot of inductance, making them way too high in impedance. Connecting the power supply cables directly to the VCC-INT power rail can cause significant resonances with the PCB PDN. To avoid this, a Vicor current multiplier module is used. The Vicor module takes a high voltage, low current input with large impedance and changes it to a low voltage, high current output with low impedance that matches the impedance of the VCC-INT power rail. The picture on the left shows the Vicor module mounted on a small PCB designed by Steve Sandler of Picotest, with a resistive load attached for verifying the linearity of the current conversion. The module is small enough that it can be directly soldered with very low inductance leads to the ZCU-104 board. The graph on the right is an impedance versus frequency plot showing how the Vicor module output impedance in black compares to the VCC-INT power rail, with the onboard point-of-load VRM turned on and then turned off. Comparison of the on and off states shows the low frequency region where the power supply is controlling impedance. This lines up nicely with the frequency range that the Vicor module can also regulate the output. The Vicor module impedance is about 3 milliohms higher, but still provides an excellent match with the impedance provided by the decoupling capacitors. The next step is to determine the types of models needed for simulating the power integrity ecosystem for the VCC-INT power rail. Models are needed for the PCB, the decoupling capacitors, the bench supply with Vicor current multiplier, and the loads package die model. There have been papers in the past at DesignCon on using measurements to extract the impedance matrix of the power delivery network, but measurements are not easy. To start with, direct one-port network analyzer measurements of impedance do not have the dynamic range to go down to the milliohms and microohms that are seen on today's power rails. A two-port shunt method is the best method, but this means separate measurements for input, output, and transfer impedance, which then need to be assembled together to create a measured impedance matrix. Instead of trying to get a measurement of the PDN-Z matrix, we will instead use an EM model of the PCB with measured models of the capacitor components. However, all models must be validated, and the best way to validate the PCB EM model is with a measurement of the bare board VCC-INT impedance with no capacitors. The picture in the upper left shows the E5061B network analyzer that is ideal for measuring low impedance power rails from 5 Hz to 3 GHz by using the S parameter ports to make a two-port shunt through measurement. The two-port shunt measurement accuracy at low frequency is improved by installing a J2012B picotest common mode rejection transformer on S parameter port 2 of the network analyzer. The two-port connection to the PCB is not ideal. Placing the connections both on the same measuring point can result in some fixturing mutual inductance, shown in the upper right picture. Placing the connections on opposite sides of a through via on the PCB avoids the mutual inductance, but now it has changed the measurement location to the internal plane layer and cancels out the inductance of the via. The impedance at the FPGA pin starts to get difficult to define. Is it at the internal plane layer? Is it at the top of a single via? Or is it the impedance seen by the FPGA with all of the power and ground vias connected together at the package pins? Comparing same-sided probing and two-sided probing in the plot on the bottom right shows the variation in inductance at high frequency that can be expected with the different measurement methods. The value of creating a PCB-EM model is that port placement is much more flexible than measurement locations. Places that would be very difficult or impossible to connect to with measurement can be a trivial port setup in a simulated model. PCB CAD data can be imported into a tool like PathWave ADS PI Pro, shown in the upper left, and simulated to create an S-parameter model of the VCC and power rail. The best way to validate the accuracy of the EM model is to make a measurement of the bare PCB with no capacitors attached. The measurement of the impedance at the FPGA, shown in the bottom left graph, shows that the high-frequency behavior is very sensitive to how the two ports are connected to the measurement point. The plot in the upper right shows the measured impedance at the bottom of a power via on the bottom of the PCB under the FPGA and compares this with the simulated impedance at the same location. The simulated and measured capacitance show good correlation, and the variation at high frequency can be attributed to challenges with fixturing and calibration on the measurement side and port setup and meshing density on the EM side. Next, the capacitors need to be attached to the PCB-EM model. But just like the PCB-EM model, it is important to verify with measurement that the data for the capacitors is accurate. Two-port shunt impedance measurements of the capacitors are done using small evaluation boards provided by Picotest. The small evaluation boards make it possible to measure the mounting inductance by shorting the capacitor pads to ground. This mounting inductance can be removed from the measurement of the capacitor mounted to the PCB using measure-based lumped models as shown here in the upper left schematic. Measurement of the mounting inductance is shown in the top plot. This mounting impedance versus frequency behavior can be modeled as a simple resistor and inductor in series connecting to ground and can easily be added or removed from the capacitor lumped measured model. Including the mounting inductance matches with measurement of the mounted capacitor. Removing the mounting inductance leaves only the remaining capacitor characteristics and is the correct model for connecting to the EM model of the PCB. The PCB-EM model is already including the PCB mounting inductance, making it necessary to have a capacitor model that does not include the mounting inductance. Otherwise, it will get counted twice. The bottom three plots compare the vendor-provided model, black dotted trace, and the measurement of the capacitor, red dashed trace, with the measured model of the capacitor with the mounting inductance removed, blue solid trace. In every case, the vendor model is closer to the measurement with the mounting inductance included and is the wrong model for attaching to the EM model of the PCB. All the capacitors were measured and models created to remove the mounting inductance. Next is creating a model for the bench supply plus Vicor current multiplier module. The plot of output impedance versus frequency on the left shows a very simple behavior. At low frequency, there is a flat 3 milliohms of a resistance. Then, at higher frequency, the control loop bandwidth of the power supply can't keep up, and the output increases in impedance with a slope that matches a 3.8 nanohenry inductor. This inductor is not a physical inductor, but rather the active inductance of the power supply control loop. This simple behavior, seen with the bench supply connected to the Vicor module, can be modeled on a schematic as an ideal voltage source in series with a 3 milliohm resistor and a 3.8 nanohenry inductor. Next, let's take a look at the package die behavioral model provided by the vendor as a simple two-port S parameter. This model captures the impedance behavior of the package and die power delivery network, making it possible to see the impedance at the aggregate of the package power and ground pins and at the die. To see how this model behaves, the package VCC power rail connection is connected to 3 different impedances, and open to see what the capacitance is internal to the package die model, a nominal 6 milliohms to represent the target impedance of the PCB connecting to the package die model, and a short to show what an ideal best case power supply does for the impedance seen at the die. The plot on the right shows the results. The simulation with the pins left open at the FPGA package, dotted red trace, shows that there is 13 microfarads of internal capacitance to deliver power at the higher frequencies as indicated by the downward capacitive slope. The short, with the dashed blue trace, clearly shows a parallel LC resonance around 45 megahertz due to the package inductance going into the die in parallel with the on-die capacitance. Interesting to note that this resonant impedance peak can be reduced, the green solid trace, by connecting a PCB PDN with an impedance of 6 milliohms that is better matched to the internal impedance of the package PDN. In addition, this exercise also shows that above 100 megahertz, it does not matter what impedance is connected to the package. The die only sees its internal impedance. This means that switching transient frequencies above 100 megahertz get all of their dynamic power from the internal package die capacitance. Now we can build the PI ecosystem model by putting all of the models together. Power supply connected to the PCB PDN with capacitors connected to the package die model. This model can then be used to look at the impedance on the VCC power rail at different locations. This plot shows the impedance seen on the VCC power delivery network at the measurement locations as well as at points that cannot easily be measured, like that of the package pins and at the die. Impedance at the VRM measurement location, the blue dash trace, is dominated by the bulk capacitors and decoupling close to the supply. Impedance at the measured location, FPGA bottom, dotted green trace, includes a single via pair connection to the VCC power rail, which has higher inductance. Both of these measurement points have too much inductance to see the impedance that the die sees at higher frequency, shown by the black solid trace. Simulation of the power integrity ecosystem model of VCC makes it easy to look at the impedance at the package pins, red dash trace, and at the impedance seen at the die, solid black trace. These two simulated locations both show an impedance peak at 30 megahertz. Exciting this impedance peak with a dynamic load switching on and off at 30 megahertz should result in a worst-case noise ripple on the power rail. Here we can see the challenge. Voltage noise ripple is impedance times the dynamic current, or the DIDT. But what is the real dynamic switching current? Is there a vendor model that predicts it? Or is it possible to measure this elusive dynamic switching current? It would be nice if there was a vendor model to predict the dynamic switching current of the load, but transistor level models of the load are rarely provided by the vendor, And even if they were provided, how accurate would they be for your given application? The better way is to combine simulation with measurement to synthesize the dynamic switching current. The next section shows how this is done by first validating the method with simulated data and then showing the results of measurement versus simulation for predicting worst-case noise ripple on the VCC power rail. The method is simple. Stimulate the model for the PCB PDN with measured dynamic voltages and let the PathWave ADS transient simulator determine the dynamic switching currents. The simple schematic shows that the dynamic voltage at the VRM can be used as the supply connection, and the dynamic voltage at the package pins can be used as the load connection to the PCB power distribution model for VCC int. By applying measured dynamic voltages simultaneously at the input and output of the PDN impedance matrix, the simulator is able to synthesize the corresponding dynamic current. Before using actual measured voltages, we will validate this method with simulated voltages. Now I will provide a demo of how to set up the model of the VCC power integrity ecosystem using PathWave ADS. The model is then used to create the simulated voltages and known simulated currents for validating the method of synthesizing dynamic current from voltage measurements. Here we go. I already have ADS open, and on the right is the ADS main window for navigating the workspace. I have opened the webcast demo schematic that is hierarchical and allows quick navigation through the setup of the PI ecosystem simulation for the VCC int power rail. Step 1 is to import the ZCU 104 board into an ADS layout window. The import also includes the stackup, which must be cross-checked with the fabricator's information to make sure that it is up to date. Once the stackup is verified, then the 3D EM simulator, PI Pro, can be launched from the layout window. PI Pro is a 3D EM simulation tool that uses net and component information to simplify the setup of an electrical analysis. The first analysis to do is a simple DC IR drop to verify the import and check that everything is working at DC before jumping to the more complicated AC analysis. I can right-click on Analysis and add a DC one. Then simply click on the VRM component in the 3D view and it will highlight the component in the design list. Right-click on the component name and add to the analysis as a VRM. Next, do the same thing for the FPGA Sync U1. Select the VCC int power rail and the ground reference. There is a warning that the VRM is not connected to the sync, so highlighting the power nets in the analysis and selecting the component connected to both quickly finds the inductor that is missing. A simple right-click on the component name and then add it as a component to the analysis. Double-clicking on the VRM in the analysis opens the setup window and the voltage is set to 0.87 volts with 5% tolerance. Next, double-click on the sync and for simplicity, set to 1 amp. Then double-click on the inductor and add a lumped model with 5 milliohms of DC resistance. The setup is complete, and next the options can be set like turning off resistive losses in the ground plane to speed up the simulation. Then the analysis is run. The simulation runs in less than 30 seconds, and the results overview shows a power tree of the voltage drops between the VRM and sync, along with additional tabular information. Opening up the current density plot shows how the current is flowing on the different layers, going from the VRM to the sync. Now that the DC IR drop analysis was successful, it can be copied to an AC analysis to create the 3D EM model of the PCB PDN. The only thing that is missing are the decoupling capacitors which were not needed at DC. These can be found by highlighting the VCC int and ground nets in the analysis and selecting components exclusively connected to both. This selects all the capacitors, and then a simple right-click on the highlighted component names, and they can be added as components to the analysis. Double-clicking on one of the capacitors shows that it already has a library cell model that was automatically assigned. Let's go see how this model was created. Going back to the ADS demo schematic, we can walk through how the capacitor model without the mounting inductance was added to the layout components. First, the mounting inductance of the capacitor measurement board is modeled with a simple series RL. Then this mounting inductance is used in the lumped behavioral model of the capacitor that has values tuned to match with measurement. The results of tuning show a good match between the capacitor model in blue and measurement in red. This lumped model, with the mounting inductance removed or shorted out, can then be compared with the measurement and the vendor model. In this case, measurement did not match the vendor model, and it is the blue trace with the mounting inductance removed that should be used with the EM model. This measured behavioral model is then added to the capacitor library component being used by the imported PCB layout. If a schematic and a symbol have been defined in the component's library cell, then PIPro will automatically simulate the schematic and load the model as an S parameter into an analysis. Now back to the PIPro AC analysis setup. In the Options menu, the frequency sweep can be extended to 1 GHz and the mesh domain optimization turned on to reduce the simulation time. Now the analysis is ready to run. The AC analysis takes 30 minutes to run, and then the PDN impedance plot is ready for viewing. PIPro uses an FEM simulator that solves for all of the ports, including the components. This means that capacitor values can be modified and optimized without rerunning the simulation. Here we can highlight all the capacitors and deactivate them along with turning the VRM off so that we can see the impedance of the bare PCB. The marker shows the PCB to have about 3 nanofarads of capacitance between the power and ground return. Next in the results is the current density. Here we show the current density on the internal power plane layer starting at 1 kHz and going up to 30 MHz. At the low frequency, the current is slow enough that it comes mainly from the supply, but as the frequency increases, the fast-changing currents start to be delivered by the decoupling capacitor locations and not the supply. The EM model of the PCB with all of the capacitor models can be exported as a subcircuit for easy use in the ADS-PI ecosystem simulation schematic. Pushing into the EM model subcircuit generated by PIPro shows the multi-port PCB EM model with all of the net name connections to the capacitor models. This subcircuit can then be placed in the PI ecosystem simulation schematic. The schematic simulation of the VCC INT power delivery network starts with an ideal 0.87 volt DC source with a series RL to model the bench supply plus bicore module. Then the PCB EM model is attached along with the vendor package die S parameter model. A 30 MHz pulsed current load is used at the die to represent the toggling flip-flops, and a steady-state DC current is added for the initial starting current. Current probes and named voltage nodes are added to output the desired dynamic switching voltages and currents. Notice that 50 ohm terminations are used to measure impedance with the S parameter simulator, just like the 50 ohm cables used in measurement. The transient simulator and the S parameter simulator are added to this schematic, and then the simulation is ready to start. The simulation finishes with both time domain and frequency domain results. Let's go back to the presentation slides now to take a closer look at the result. Now you have seen how the power integrity ecosystem model is built for VCC INT. Let's see what the results are for a known 30 MHz switching load at the die. voltage and current simulator probes are placed at the VRM input side to the PCB PDN and at the output of the PCB PDN at the connection to the package pins. The simulation is run with an 0.87 volt DC supply and a known dynamic 30 megahertz switching load current. This simulation provides the dynamic voltages measured simultaneously in time at the VRM and at the FPGA pins. It also simulates the dynamic current going into the FPGA. Now, if our method for synthesizing dynamic current really works, then we can take the two dynamic voltages and run a second simulation with just the PCB PDN model to produce the same dynamic current result at the FPGA pins as this full PI ecosystem simulation of VCC-int. Let's give it a try. Here is the setup. The simulated voltage at the VRM is used as a source on the VRM side of the PCB PDN, and the simulated voltage at the FPGA is used as a source on the FPGA side. This fixes the dynamic voltage across the PDN impedance, and when the simulation runs, the current probes record the synthesized dynamic current. The question is, will it return the same dynamic current that was seen in the full simulation with the known 30 megahertz switching load? The answer is yes, it worked. Here, the synthesized dynamic current is in blue, and it overlays very well with the original simulated dynamic current from the full power integrity ecosystem simulation. It even captures the startup transient. The term synthesized is used to help distinguish between fully simulated results and this special case where the measurements of the system are used in combination with the models to synthesize a result. Here is a look at how the board was set up for the measurement. The bench power supply replaces the onboard VRM, but it cannot be directly connected to the power rail. Instead, a Vicor current multiplier provides the necessary low impedance connection with 0.87 volts and 30 amps. The Vicor module is mounted as close as possible to the ZCU104 PCB using copper braid to keep the resistive losses and inductance as low as possible. A Rogowski current probe is attached by wrapping the thin wire loop around the copper braid connection to the VCC-int power rail. This small current loop probe avoids disturbing the low impedance connection of the Vicor module to the VCC-int power rail. The picture shows the FPGA soldered to the PCB. Obviously, there is no way to directly measure the current going into the FPGA package pins. The good news is that it is easy to measure the dynamic voltage at the VRM and at the FPGA. The same matched length coaxial cables used for the two-port shunt low impedance measurements of the PCB PDN can now be used to measure the voltage. The coax connections are 50 ohms, which is high compared to the power rail impedance, providing a high impedance probe connection. The oscilloscope calibration to deskew the ports and fixture cables with matched length and equal delay ensure that the dynamic voltages are measured simultaneously. The method of synthesizing dynamic current was validated with simulated voltages, but it is also good practice to cross-check the method with an actual measurement of dynamic current. This comparison of measured dynamic current versus synthesized is done with the load toggling at 200 megahertz to provide a large 10 amp step load in the steady state current. This large step load is easy to pick up with the Rogowski AC coupled current probe at the VRM and can be used to check how well the synthesized current correlates. The plot on the left shows the AC coupled oscilloscope measurement of the voltage at the VRM in green and the voltage at the FPGA in gold. The Rogowski probe tracks the rapid rise in current that causes a droop in the power rail voltages. The plot on the right shows the synthesized current in pink at the VRM with similar behavior. Now that the synthesized current at the VRM has been validated, and we have confidence in the result shown in the plot on the left. The next step is to look at the synthesized current at the FPGA. The plot on the right shows the dynamic current at the FPGA in blue compared to the dynamic voltage in orange. Notice how quiet the steady-state dynamic current is going into the FPGA at 200 megahertz, even with a total current of over 10 amps. The 10 amp step load caused an initial droop, but after all the toggling flip-flops get turned on and the power supply catches up, the steady-state dynamic current is quite small. Now we have shown that the method works. Let's use it to investigate worst-case power rail ripple and see what the dynamic current is doing. The impedance plot shows an impedance peak at 30 megahertz due to the parallel resonance of the package inductance in parallel with the die capacitance. Voltage ripple is the impedance times the dIdt dynamic current. So the prediction is that if the peak at 30 megahertz is excited, it will create more voltage ripple than the load switching faster at 200 megahertz with 4 times the current. But this assumes there is the same dynamic current at both frequencies. Is this true? Let's go find out. Going back to the model of the power integrity ecosystem, we can use it to predict the difference between the steady-state dynamic ripple at 30 megahertz compared to 200 megahertz. The ripple on the left with 30 megahertz toggling of the load draws only 2.5 amps, but has twice the peak-to-peak voltage ripple of the load switching at 200 megahertz with 13.5 amps. This is a good prediction, but we had to guess at the model for the dynamic switching load at the die. Now with our method for synthesizing the elusive dynamic current, it will be possible to compare both the voltage ripple and the dynamic switching current to get a more complete picture of the noise power density at the FPGA package pins. Let's see if measurement confirms our prediction of worst-case steady-state ripple at 30 megahertz. The results with the FPGA load toggling at 30 megahertz for the synthesized dynamic switching current at the VRM and at the FPGA are shown in the top 2 graphs. The plot on the left with the measured dynamic voltage in green and synthesized dynamic current in pink at the VRM shows that the steady-state dynamic ripple current is on the order of milliamps at the VRM. However, the plot on the right shows that there is a significant dynamic current at the FPGA pins as indicated by the blue trace, and it increases to close to 2 amps peak to peak as the number of flip-flops get turned on and toggling. The dynamic voltage is also increasing, the gold trace, and matches our prediction for worst-case voltage ripple at 30 megahertz. Now remember that the voltage ripple is the spectral content of the current times the impedance. Now that we have a real measurement of the dynamic switching current at the FPGA, it is easy to take an FFT to see what that spectral content looks like. This is shown in the graph on the bottom right. The spectral content of the dynamic switching current is not constant. It has a peak at the toggling rate of 30 megahertz and at the subsequent harmonics. Zooming in on the VCCN power rail dynamic voltage and dynamic current at the FPGA package pins provides a nice comparison between the 200 megahertz switching FPGA load on the left and the 30 megahertz switching load on the right. The measured data confirms the simulated results that predicted the worst-case power rail ripple at 30 megahertz. What is not intuitive is the much larger increase in dynamic current for the worst-case 30 megahertz switching load. The dynamic current ripple is orders of magnitude larger than what is seen at 200 megahertz, while the voltage ripple has barely doubled. This synthesized current provides a real look at where the current is flowing in the power delivery network as the source of power changes from the power supply at low frequencies to the decoupling capacitors in the middle range, and then to the internal package die capacitance at the higher frequencies. The success of measuring the dynamic current at the FPGA makes it possible to consider synthesizing the dynamic current at the die by using the synthesized dynamic current and measured voltage at the package pins. In fact, this was how the initial model of the switching load was refined in the power integrity ecosystem simulation for VCC-INT. Initially, just a simple pulse width modulation of the current load was used to match the steady state current that was observed. But after synthesizing the current at the FPGA pins, it was possible to modify the rise and fall times of the steady state switching load. The modified rise and fall times provided a better prediction of the dynamic current synthesized at the FPGA pins. This brings us to the end of the presentation, and I would like to leave you with the key findings from this effort. First, a bench supply can be used to power a high current, low voltage milliohm power rail, but only if the connection to the power rail is matched in impedance. An easy way to do this is with the Vicor current multiplier. Second, modeling the PCB power delivery network requires measured models of the components and EM models of the printed circuit board to accurately capture the distributed parasitics that are significant when modeling power rails with milliohms of impedance. And third and final, the real success was the demonstration that simultaneously measured dynamic voltage measurements across a known PDN impedance can be used to extract the elusive dynamic switching current on the FPGA power rail. I wish you success in finding the elusive dynamic current on your next design. That concludes our presentation. Now, on to the Q&A. For that, I would like to bring in my colleague and get to your questions.
Great. Thanks so much, Heidi. Now it's time for the question and answer session. If you would like to ask a question, click on the Q&A icon at the bottom of your console. We will try to answer these during the webinar, but if a fuller answer is needed or if we run out of time, Heidi will answer it later via email. So thanks, Heidi, in advance. Please know that we do capture all of your questions. So Heidi, here's the question from Ryan. EM simulations can be challenging. Is it difficult to set up the ports and models for all of the capacitors components and get this connected correctly in the schematic?
Good question. Traditionally, EM simulation setup has been challenging, but with newer tools like PI Pro and PathWave ADS that are net-based with automatic port placement, it is much easier. Importing from ODB++ or .brd board files brings in all of the net names, stack up, and component information to allow setup in a matter of minutes rather than hours. The simulation of VCC-INT was able to run on my laptop with only 32 gigabytes of RAM.
Great, thanks. And here's your second question. This one comes from Grant. Does PathWave ADS make it easy to use measured voltage waveforms in transient simulations?
Yes, ADS has a few ways to use measured voltage waveforms as a source in a transient simulation. But the easiest one I found was a simple data set defined source, and even very large megabytes of data can be simulated. The other thing I found very helpful was using the deep memory of the Infiniium oscilloscope to save very large data sets, and then using the Infiniium offline software running on my laptop to select smaller subsets for use in simulation.
Great, thanks. Okay, Heidi, here's your next question. This one comes from Bert. What is the title of the DesignCon paper that was delivered on this topic?
The paper was delivered on this topic. We did this back in January at DesignCon 2020 with Steve Sandler of Picotest and Jack Carroll of Xilinx. And the title is a method for dynamic load current testing with a benchtop power supply.
Great, thanks. And then we have time for a couple more questions. So this question comes from Nicole. I am new to power integrity and have not heard about the method of modeling capacitors with two-port shunt impedance measurements. Where can I find more information?
Great question. If you want to learn more about how we created the measured models for the capacitors with the mounting inductance removed, the best place to start is with the Keysight-sponsored YouTube video with Steve Sandler of Picotest. He did a great job on this one, and the title is How to Design for Power Integrity, Measuring, Modeling, and Simulating Capacitors. The link for this How to Design for PI YouTube series is, let's see, I'm sorry, I got a mouthful here. The How to Design for Power Integrity YouTube series is included at the end of this webinar, and and the one that we're talking about here about capacitors is the third one in the series.
Yeah, and all these YouTube videos are also 10 minutes each and application focused, and they have a workspace too. So that's very good. Thanks for sharing that resource. So here's your last question. This one comes from Eli. This is an interesting use of measurement and simulation to synthesize a result. Do you see any other uses for this?
I mentioned the possibility of using the simulator to synthesize a better estimate of the actual dynamic current at the die, but another topic I'm very interested in right now is conducted EMI and EMC type applications. So I am also interested in seeing if this can be used to look at conducted and radiated EMI without having to run complicated SPICE models of the load or VRM, which vendors are very reluctant to divulge those actual SPICE models.
Okay, great. Well, Heidi, thank you so much for your presentation today. And before we close, any closing comments?
Yes, I actually would like to acknowledge my co-authors from the DesignCon paper, Jack Carroll and Steve Sandler, Jack Carroll of Xilinx and Steve Sandler of PicoTest. A lot of hard work and effort went into this topic. And then I also would like to thank the audience today for attending the webinar. Thank you.
Great. Thanks so much, Heidi.